Alright kids, welcome. Our next lesson on tap is section 1.3, continuity and behavior and limits. Alright, this is a pretty note heavy section, so we'll get right into it. So, first on the docket is the following. Okay, so what we have is what the definition of a continuous function. We've talked about functions previously, but what is a continuous function? A continuous function has a graph which contains no breaks, holes, or gaps. I.e., you can trace the graph of a continuous function without lifting your pencil. So you just put your pencil on the ground and you go, you know what, I'm going to trace this graph, and away you go. This is a continuous graph here. See how I'm not picking up my pen at all? It's just going like that. That's a continuous graph. But we have some situations where we don't get into the continuous graphs, which we will talk about in a second. Speaking of talking of those, we have one big definition. Now, this is going to become important for what we're going to be doing right now, but it'll be really important later. So it's the concept of limits found on page 24. Now, this is a wordy definition. We are going to get into limits much heavier later on in the year. We're not going to do a ton with them right now. However, your book does refer to most of their definitions from here on out with a limit definition, so I do want to explain it. So if the value of f of x approaches a unique value L as x approaches c from the left side, then the limit approaches that. What does that mean? All it's saying is like, hey, the limit as x approaches some number. It's saying, hey, if I put in x into this function, I'm going to get back this value. That's all it's saying. So it's saying as I approach this number from either direction, I end up at the y value. So it's saying if you put x in, you get y. Now, how has that become important for us? Because we have limits at infinity. It's saying, hey, as x goes to infinity, what the heck is my graph doing? That's where it becomes important for us right now. Because we have three types, going back to the previous slide, of discontinuities. What's that mean? We have continuous function, right? Well, based on my limit definition here, we're going to have three types of things where a function is not continuous. We have three types of discontinuities. The first one is what we call an infinite discontinuity. What does that mean? It means both graphs go on to infinity. Mathematicians aren't really great at naming stuff. So this example of this is, remember these, an asymptote. Asymptotes are examples of infinite discontinuities. So the graphs they could go the same direction, they could both go different directions. But they are going to infinity. The up arrow and down arrow we talked about yesterday. The next type of discontinuity is called a jump discontinuity. Now, why is it called a jump? Because as I move along here, I'm literally going to have to jump to get to my next point. Now, this happens, if you recall from Algebra 2, piecewise functions have a ton of jump discontinuities, which we will be doing some this chapter. That's the type of function being discontinuous. That means I can't physically do this. I have to lift my pencil up and go to here. Now, the last discontinuity we have is called a removable discontinuity. That means I have a graph everywhere, except I have a tiny hole here. It's like a gap in the floor. So it's like, this is going to be a problem for me. I can't do anything about this. It's a hole there. It's a hole I can't do anything with. And example for this is when we factor, we can get rid of these holes. It's a removable one because we can physically take that discontinuity out of my graph, which we will go through an example currently. So there's three. We have infinite, we have jump, and we have removable. So, what does it mean to actually be continuous in terms of definitions? So, a function f of x is continuous at some x value if it satisfies the following three conditions. It's defined at x, means that you have a value for the function at x. So, for example, I can't simply say that, hey, is a function continuous like the function 1 over x? Is it continuous at x equals 0? No, it's not, because is that function defined at x equals 0? If I put 0 in, I've got a huge raging problem there. I can't divide by 0, so no good. The second thing, a function f of x approaches the same value from either side. That means that you have to go from the left and from the right meet at the same point. And third, the value that f of x approaches from each side is what happens when you put c in here. So what the heck does that mean? This is on page 25 in your book, by the way. So an example. Let's say I have a graph that looks like this. And I have some function here. And this is my c value, and I have a big old hole here. But what I do have is I have a point. It's a piecewise function. And there's my point right there. Piecewise, it still passes the vertical line test here, but there's my value up here. So, look, is f of x defined at x? So, at x equals c. Sure it is. It's that purple point right there. F of x approaches the same value from either side of x. Sure it does. Look, as I come from the left here, and from the right side, I approach that hole. So, obviously this is not continuous, right? Because I have to lift my pencil to tap that point, which is where condition 3 comes in. The value that f of x approaches from each side is that c value. Is this value the same as that purple one? No. So that's why this function, obviously, is not continuous. So just because it satisfies one, it must satisfy all. So that's really important for us. So, let's move on. Now, what's an example of a question? So what a question could ask you is this. Hey, I want you to tell me, based on this function right here, at these two values, is this function continuous? And if it is continuous, that's great. If it's not continuous, tell me what type of discontinuity I have. So, we've got our 3 discontinuities, remember. Scrolling back here. We've got infinite, jump, and removable. Jump really only happens in piecewise functions. So what I've got to look at here is, am I going to have an asymptote, or am I going to be able to factor something and remove it if I have a discontinuity? So let's look here. So I have 2 things I could do here. One, at x equals -6. So I put in -6 into this function. If it works out to a number, folks, then I'm golden. Then I'm great. If it doesn't work out, then I've got to see if it's going to be continuous or not. So we put this in here, and I've got 0 divided by 0. That's a problem. We'll deal with that in a second. The other value that I want to check is x equals 6. So put 6 in here. And tell me what I get. That's what we're going to have to do. And see what happens. So when I do this work, I get 36 minus 36 over 12, which is 0 over 12. Well, guess what? I can divide 0 by a number. So it's continuous there. It is. Why? I didn't get anything goofy like dividing by 0. And in fact, I'm going to get y equals 0 there. That's the answer. So now back to this problem over here, that -6. So what I do, obviously it's discontinuous because I can't divide by 0. So what do I do then? Well, we go ahead and factor the top portion. X squared minus 36 factors as x plus 6, x minus 6, difference of squares. Can I cancel anything? Why, sure as shooting can. They're linked with multiplication. Goodbye, x plus 6's. Now I've got left x minus 6. So I cancel out the pluses, and I'm with the minus. Now, try it again. If negative 6 doesn't work now, we had an asymptote. It's a infinite discontinuity. If I can put negative 6 in here, which I can, that works out, right? To negative 12. It's called a removable discontinuity. Why is it called that? Because I literally removed it in the problem. It was an issue here, I factored some stuff, and now it's not a problem. So I removed the discontinuity. It's not as bad. So it's discontinuous, but it was removable, or a hole. So that's a good thing for us. The next thing we're going to cover is end behavior. End behavior, pretty simply, is talking about what the graph does at the end of it, which means as x goes to positive infinity or negative infinity. I want to know what the graph is doing, like what is y doing? So, for example, let's look at one of these. So, describe the end behavior of the following graph. So, here's my graph here. So as x is getting really big or going to the right, what's y doing here? So as x approaches infinity, and this is where you have the limit comes in. The book will define this as the limit as x goes to infinity. What happens to y? Well, where's my y going? Well, it's going up. Forever. Forever. Good movie reference there. So y is also going up to infinity there. Now I need to look at as x goes to negative infinity. So as I go really far to the left, what's my graph doing? Where's my arrow pointing? That's always what you want to find out. Where is my arrow pointing? As I go to the left, my arrow is pointing up. So my graph also goes to positive infinity. So as you put really big values of x in here, really big values of x, you're going to get back infinity. As you put really tiny values of x, like negative 2 billion, 3 billion, y is going to go to infinity. Now, what if I didn't have a picture? And we'll talk about some of that later. But if you didn't have a picture, folks, we're going to be able to figure out end behavior solely based on this equation right here. That's right. We can use the equation they give us to tell us about end behavior. So, thus ends this wonderful and glorious video. Yay! Hope you enjoyed, and now you are ready to tackle the future. / tackle this lesson.